behind.
Yes, please. For us who have just joined, we are
Mm.
just beginning right now. We are seeing this graph with voltages, and we have no idea about that.
Okay. Yes, in the call, is there someone who has got the concept? Can I also know if someone has gotten the concept? Who got the concept? Who got the idea of what I was talking about? Hello, Joshua, Ivan, Adrian, Dennis,
I've also
Bagonza,
just
and
joined.
others.
I've also just joined from the other link, so I haven't really no idea.
Oh,
Me too. I have just joined it.
okay. Bernard, you've been in this call from minute one. Did you get the idea of what I was talking about? Bernard, are you on? Hello? Okay. So for the people who have just joined, we hadn't moved so far. Let me just redo this again. Um, but this is your second lecture. Did you attend the first one?
No, I didn't attend.
Who else didn't attend? Oh, okay, okay. Jean and who and Michael only. The rest attended the first lecture, right?
Me, even Dennis didn't attend.
Dennis. But you accessed these notes or something like that. Did you access the first lecture notes, slides?
Yes.
Okay. When you went through, what didn't you understand in specific? Because we're still looking at the introductory concepts in digital electronics. And earlier in that lecture, maybe just to give a little recap, because I think many of you will say I didn't attend and all that, but it's also a good idea to look at what colleagues covered and maybe seek for clarification just. So we looked at, in general, how digital signals are differing from analog signals. And we said analog signal is simply a continuous signal, while a digital signal is actually in form of discrete or in steps, um, and it doesn't work within continuous values like the analog. So the analog has no breaks, it is only continuous. And we gave different examples of analog representation, like the speedometers that are in the old cars, the old mature thermometers. But the ones that you see just blinking, those are digital because they just have values to change in discrete steps, even the digital clocks that you see. We also looked at things like a fuel gauge, which is in modern cars. Okay, and later on, we looked at the disadvantages and advantages of using analog and digital signals. Some of the advantages of using digital signals, we said, In digital signal, you can easily store information and even for a longer time and in larger quantity. And also that you can minimize greatly the noise in digital, where it is very hard to minimize noise in analog. But some of the disadvantages that we looked at in the digital are things like quantization errors and also the processes in conversion from analog to digital being very many. So it takes time to have your digital representation. So when I talk about quantization error, if you look at, maybe I could leave this board. I have another one here. So assuming you have your input here, and you're saying you have your analog signal here. This is the analog signal. Your output is going to be here, and what you need as output is a digital signal. So you would always have something which is called a converter, and this converter is called analog digital converter, abbreviated as this ADC. Okay, sometimes they just write something like this AD. That means that analog digital converter. So this is the input where you have the real world information, uh, because it comes in form of sound waves like this, continuous what signals. So when it is processed and represented as digital, you'll have um, something like this. The signal was this originally, okay? Signal was something like this originally, but when they try to uh, sort of process it in digital, it is just like steps, and these steps are what we call the zeros and ones. So when you see me bring the marker down, it means that is a zero. When I take it up, it is a one, down a zero, up a one, down zero, like that. So you see, I'm trying to redraw or try to guess the path of the analog signal. So this process is so long. Okay, so this is what is actually done uh, during this process here by the
Coordinator.
ADC. Yes, please.
It did the same way as
You are off. Hmm.
making like pulses.
Yes.
Okay.
Mm.
Thank you.
So I'm trying to show you what really happens when uh, when this step is actually taking place. This step here of the analog digital conversion. This is what exactly what happens. It tries to redraw or guess uh, the path of the input signal, which input signal was analog. So in so guessing like that, it makes those pulses, and the pulses we say we only count a pulse when we see the signal is up, then that is a pulse. And when it is up, that is a one. When it is down, it is a zero. Okay? These are zeros down, these are zeros down, this is a 1, 1, 0, 1, 0, okay, to the end. So at the end of the day, you will have your final output represented um, by use of what is called a timing diagram, which is now clear representing that at this point of time, the signal was low. Maybe this was T1, this was T2, this was T3, this was T4, uh, T5, T6. Okay, so at this point, signal was like that. Okay, like this. Maybe this time stops there and then comes back like that. So wherever you see the thing is up like this is what we call a pulse. Okay, this is a pulse, and that pulse we say the signal is high. Okay, it is high. Here, when the thing is down, the signal is zero, and we say it is low. The voltage is low. It means that the state is off. This one is on, like that. So that is going also like that. Is that kind of clear? Does it make
Yes,
sense?
yes, this is clear.
Okay. So back to this. We are saying that in kind of doing that, this way of processing, you realize that we need to follow the real timing. Just imagine that our original pulse here, which was, our original signal, which was analog, maybe this time was T1, this was T2, T3. As we try to redraw using the ADC converter, we don't want to put to another timing. Maybe assuming this was T3, but when you're trying to redraw, okay, when you're trying to redraw your pulse, okay, maybe when you reached here, the thing tried to go off. So it is not trying to synchronize well. So that is one of the disadvantage that you could find in digital representation, that signals are not sometimes synchronized well. So we say that one of the disadvantages are synchronization issues. So you can say synchronization issues, synchronization errors, or quantization errors. Okay, so quantization comes again from how you wanted to make your things run in the same times as earlier pictured. So I was trying to actually explain to you the disadvantage of digital signal is that we say in digital signal you can find quantization errors. Um, Another disadvantage, we say the process takes time. Then for the disadvantage of the analog, there is analog signal is prone to noise, is prone to electromagnetic interference. Okay, some of you have maybe been in theaters, maybe someone is speaking with a microphone, and when that person maybe moves close to the speaker, have you heard that kind of interference that comes in? Who has had that kind of experience? Hello. Yes, apart from Paul, is anyone who have had that experience? Someone is speaking on the microphone, and when they move close to the speakers themselves, you hear that kind of interference. So that is most common if you are using those microphones that are actually um, just analog microphones, because a microphone is actually a typical example of an analog device. Okay, that is not so common on digital systems. So another disadvantage of analog signal, um, what else did we talk about that? Um, okay, I think you will find many in the next lecture, I think. Um, we are in the first lecture, the real comparisons. I think somewhere I gave a full table of about the differences. Yeah, but at least if you could remember that the analog signals are prone to signal noise, and actually also the interpretation errors are also very common in the analog, and also you cannot easily store information in the analog. Okay, yeah. So allow me now to switch to lecture 2, if you have got a brief concept about what we covered in lecture 1. Can I move ahead? Okay. So we are saying that the 0 and 1 is our main focus. As long as you understand where you have to use a 0 and a 1 here, then the second lecture is done. So I'm going to draw a sample table here. Uh, so this table is a way how and what we'll call our digital values or signals. So many times you're going to find these words, but use them interchangeably according to the situations, but they will be meaning the same things. So when you find a zero, when you find a zero, it means this zero is the same as a low voltage. Okay? So even when you're programming, that just means that this is low what? Voltage. The signal is low. And it means if the signal is low or the voltage is low, then that state is off. If it's a Boolean, then Boolean also takes on two values, either false or true. So for a zero voltage, for a low voltage, for an off signal, the Boolean is always a false. Then the other side, if the logic is 1, then the signal we say, I mean the voltage we say is high, and the state is on, the Boolean is true. So you're going to find a lot of these. Use them interchangeably, but depending on the situation. Someone raising up their hand. Yes, Joshua. You have a question?
Yes, please.
Mhm.
Is there any way you can represent the logic of a signal in terms of Boolean values such as false and true?
Yes. This is what I'm showing you in the table. Are you seeing this table?
I'm seeing it.
Are you seeing this last row? This is for Boolean. So is it clear now?
Yes, it is clear.
Okay. Um, so um, if you have seen, yes, I said someone could help me allow people join the meet. Who was the co-admin? Suzy. Oh, you're there. Okay. Okay. So please allow them. So you all have laptops, or you have seen such a symbol on your power buttons. I'm meaning this symbol here. Have you seen this symbol before? Aha. So it has two things. It has a one, but it also has a zero in its what? Representation. This means that when you press this button, when you press this button, either the device is going to go on or off. So if it is off, then what is in play is the zero. If it is off, that means that you have set the voltage to go low, right? And if that circuit or device is on when you have pressed that button, that means that you have set the voltage to go high. Okay, you have set the voltage to go high. So in terms of pulse representation, we said that there is what you call a timing diagram. Your high signal will be represented like this. Okay, in that case, it will be what? Looking like that. Means the signal is high or the state is 1. Okay, if it is on. Um, so depending on the technology, if you have maybe looked at those hybrid cars where there are many automations, for example, even if you have pressed just a button somewhere and then uh, the door opens or you have just inserted the key, yes. On another situation, maybe when they have used the key and when they insert this key and they set the signal to go to the 12 volts. Of course, that means that they have set um, the the voltage to go high. That means that it is telling this door to do something, either to lock or to open. Okay. So just depending on the technology, but as long as you have understood the underlying idea of the zero, where the zero is working and where the one is working, or the high or the true, then you're good to go. So the different devices or systems will consume different power. Sometimes if you find a device may be um, consuming maybe 12 volts, if maybe you have 12 volts here, that is the maximum, okay, that it can consume of the operating voltage. Uh, the designer, when he's programming this device, he will maybe set that the range from 0 to maybe 8, all this range will mean that the circuit is off, or the state is low, okay, or 0. And then he sets maybe that between let me say 10, yes, 10 to 12, this circuit is going to be off. But then there is this what? Invalid. I mean, there is this unused. We call them unused ranges. So this unused range, which is from 8 to 10. So as long as the signal will go into this range, the circuit won't know that I have to switch on or off. Okay. So if you leave it like this and you don't use it, that means that you are letting your circuit to think for itself. That sometimes I could go on even when the voltage is 9, but another time I can go off. Just a second, my battery is going to get off. Let me get a charger here. Hello, hello. Yes, so I was trying to explain um, that think I could uh, do this again, no problem. So I said that if you have a device and its maximum operating voltage is maybe V max of 12V, um, the range for it to go on is between 10 to 12V. It means that this one will be high, and then maybe the range for it to be set to low is maybe from 0 to 7, to also mean that this range will be low. So the remaining portion here is unused by default. So when you're programming this device, you will need to force it to either uh, by default this range also be either a high or a low. How would you do this? You would make use of what we call a pull up resistor or a pull down resistor. When you use a pull down resistor, it means that you are going to connect a resistor to the ground and then back to your pin which takes in the signal, okay, such that by default this line here is a zero or is a low. That is when you're using a pull down resistor. On the other hand, if you're using a pull up resistor, you are by default trying to set that input line to be high or to have a signal of 1. And in that case, you will only connect a resistor which is coming to the input of your circuit, okay? And this resistor will be connected to uh, the voltage which is already up, because you see with circuit you always have two wires, okay? You have a live wire and a ground wire, which is earth, okay? So I'm meaning that this will be the positive line, this will be the negative line. So if you connect the resistor to the negative line, by default you are making the signal go low on that input. If you are connecting the resistor to a live power, I mean to the positive power or to the high voltage, that means that you're letting that input line to be high or to be with 1 by default. Why do you have to make this? You want to uh, avoid fluctuation of power, because sometimes power is not stable. Sometimes if you were supposed to receive uh, maybe a 240 volts in your power circuit or the main, you find that maybe sometimes this power is fluctuating from maybe 200 voltage, sometimes goes to 210, sometimes again even more than the 240. So if this happens, then also your DC, because your equipment most of the time are going to be DC, which is direct current, it means that it wants to allow only 12 volts to pass through. But in that case, it may not even be able to push um, up to up to even 10. Now, it won't know, the circuit won't know that I need to be a high in this range or a low in this range. So you want to eliminate those fluctuations which actually can cause noise. Okay, so in the earlier minutes, I actually said that this concept you might not find it so relevant unless when you reach at the point when you're actually programming a digital circuit on your own. But I wanted to make this idea a bit clear like that. I don't know if it makes sense or if someone has a situation like that. Some things, when you're learning them, you actually don't learn them just in just one day, but you build concept by concept. So in this slide of mine, I actually try to explain the same using an example where I had 5 voltage as maximum. And in this situation, I said that the range from 0 to 0.8 might be the range where I want to have my low signal. That is why I wrote binary 0. And then the range between 2 voltage to 5 voltage is a binary 1, which means that the signal here should be high. But the range between 0.8 to 2 um, is an invalid what? A voltage range. So this means that if you leave this one unconnected or uncatered for, sometime when even voltage is 1V, sometimes the circuit will go on, and this will not be good. I can give you an example, or I can ask if any of you have ever experienced this. Do you use, is any one of you, of course, actually not any one of you, but at least most of you are now using these bulbs that are called LEDs that are even 5 watts, maybe 10 watts. Most of these bulbs, sometimes when they are connected to a house which is not actually finely wired well, sometimes when the switch is off, you see this bulb trying to blink a little bit or trying to be dim. It is not actually on, but it is showing that it is having some little current flowing through, although the switch is off. Who has faced such a situation? Okay, Paul. Who else? Joshua, Emmanuel. Yes. So one of you could maybe discuss about this. What did you think about that bulb? Did you think the bulb was dead, spoiled? What did you think? What was your scenario? Can I hear from Paul? That is what you thought. That is interesting. Eric, what did you think about that? Okay, Emmanuel, what did you think?
Sometimes I just think maybe there could be a problem with the wiring.
Mm-hmm,
Maybe there's a wire that is not stable, tightened.
mm-hmm. Yes,
Yes.
Michael.
Thank you. For me, I thought when the bulb is blinking when the switch is off, I thought the bulb was getting spoiled.
Uh-huh. So, I got an opportunity to study some electrical engineering. The real idea is this: is that you know when even when you power off, or someone was trying to say something. Ah, you are just joining. Okay. So I was saying um, that you see these are our electric poles. Okay, where you get your, okay, of course, this is where you have your Yaka meter. Okay, your Yaka meter is actually on the pole, and many people don't know that what you have inside your house, what you have inside your house, maybe this is the main switch. This is the main switch, and of course, anything comes and uh, you have maybe your now Yaka, you what you call the meter, but me I call it the user interface. Okay, so this is just the user interface where you guys have buttons, you press buttons and then enter your token. It may either actually be wireless or a wired uh, Yaka interface. The real meter is on the pole here. Now, uh, power is going to be continuously coming into your house, and you're going to have maybe uh, the socket, okay, the socket, and I'll call them the mains. Okay, when you switch off your power here, when you switch off your power here, and maybe, yeah, now in this case, let me just say, okay, this is the switch to your bulb here. This is the switch to your bulb here. Some current, some current, because of course it moves from negative, I mean from positive going through negative, like that. So some current will still be going through even if you have switched off. Okay. Now, what you see that there is some kind of blinking like this means that if your main here, if your main here, and with the whole wiring of the house, they didn't include those pull down resistors. Okay, if they didn't include the pull down resistors to the ground, uh, this line here will assume that even though this bulb requires, let me say, 12 volts to go on, if it requires 12 volts to go on, and below the 12, maybe you have 19.9, this one maybe would be off. Okay, if it will be off, then above 20 it will be high. So if you lack the pull down resistor, it will assume that sometimes this signal is high between this range of maybe 19.9 to maybe 15 volts. So that kind of switching is now being caused by the remaining current that keeps on coming through by default, because it is analog signal that is coming in. But if you included the pull down resistor, it will set this range to to default low or default zero. So you cannot see the situation that when, even if you have switched off this bulb, it can try to blink. But also the other situation can be that the bulb is soon getting spoiled. So it can no longer it can no longer feel the presence of the other resistors, the pull down resistors. Are you trying to get my point a little bit?
Sir, the chat isn't available. I don't know why. And also, I'd like you to help us and someone helps record this session. Thank you.
This session is recorded, and also I would want to inquire from others. Are you able to see my screens or what? And so, uh, do you think she has an issue with the network? Bagonza, could you try to maybe leave the call and then join again? You could be having a network issue.
Okay, please.
Okay,
No, actually, the chat is not available. It's not working.
sure.
Yeah, you can't type anything.
What are you meaning? The chat or my screen? Michael, what's the issue?
It is the chat. The chat
Actually,
isn't
the,
available.
actually, the chat is not working. You can't type any message and send.
Now it's available.
It is activated now.
I think it's network, guys. I don't control the chat at least.
What they are trying to mean, they want to type messages here and send it.
Yeah, but I don't again control the chat. I don't control the chat. But when the network is maybe an issue, it can disable
But now
and
it
then
is fine.
activate it again. Yeah, I actually did nothing. I did nothing.
I'm the one who activated it.
You don't activated it.
Yeah.
Okay, okay. So let's proceed, please. Um, yeah, in brief, I said again that signals could either be represented by sine waves. A sine wave is something like this. Sine wave is something like this, but also like this. Now, the timing diagram, most cases are representing the digital signal. It means that here would be a 0 and this would be a 1. Here would be a 0, here will be a 1. Okay? So that is the need for timing diagram. And when you take time and read through this section, you realize that I say that timing diagrams are very important in showing the relationships over time between many digital signals. So we cannot talk about timing diagram in an analog signal. We use them in the showing the relationships in between the digital signals. And when we come to the clock signals, they are very important in ensuring that specific parts are actually syncing with each other. Because we need the clocks when you are designing maybe systems like the traffic light systems and all that. Because we want to make sure that each and every activity is in their real time. Okay, now there is what we call periodic and aperiodic signals. Aperiodic signals are those signals that are actually not regular. They are irregular, and it means that they cannot repeat each other. Let me show an example here. Um, if I have two graphs here, so in my definition, I want you to tell me this is time, this is time, this is voltage, voltage, do like this. Oh, I have to start from zero. I need some contribution. Um, this is A. This is signal A. This is signal B. Which one is the periodic signal and which is the aperiodic signal? I have signal A, I have signal B. Huh. Let me see who wants to answer. Yes, Paul. So you call which signal as this, the CSB? Okay, good try. Yes, let me hear again from who was that other person who was raising their hand? Edwin, was it you?
Yes, it was me, but I had the same answer.
Okay, and Michael?
Thank you. According to me, chart A is periodic and chart B is aperiodic. Why? Because
Oh,
chart B repeats, the wavelength repeats itself.
at regular intervals. Okay, yeah. So yes, someone else wants to say something. Yes, Michael. Michael.
Yes, I've already given my contribution.
Okay, so I think that is so clear. That is so clear. So when you're answering such a question, kindly you can even include some illustration like that. Don't just write things. Okay. Okay. So that's about that. And why are they important? Of course, in digital systems, we often need to keep our operations very smooth, and you don't want to have things vary. So you need to know when to use the periodic and aperiodic signals. So an example, if you want to mimic um, a periodic signal, is just look at the way the clock works. That ticking thing, the t, 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 it counts each and every second. It will never count and then you assume that this time it has maybe taken longer. Okay. Yet if they tell you to actually clap, uh, uh, accurately you may not keep the same time. Okay. Then this brings us to other concepts like period and a frequency. Um, yes. So let me start with. I think let me start with frequency. So I'll say maybe this is maybe 0.2, 0.4, 0.6, 0.8, and 1.0. This is time in seconds, and I'll call it this. Let me call this amplitude. Okay, amplitude in terms of voltage. Um, and I will say um, if I draw signal here, so I'm not an fine artist. I draw this like this. Of course, this one have to complete the cycle. Now, there are very many concepts that you need to understand here. From this point to this point is is a whole cycle. Okay, from this point is a cycle, and again from this point to this point is another cycle. Again, from that point to this point is another cycle. So when we talk about, first of all, actually let me start with a period. Okay, a period is going to be the time the time taken here to complete this one cycle. Okay, this time taken is called a period, and we denote this period as t. Also, the time from here to here to complete another cycle is going to be period t, and also to complete another cycle here is going to be a period t. So when one asks you to define a period, you could elaboratively tell them that period is that time taken to complete a whole cycle. And I've shown you how a cycle um, looks like. You have to complete um, the time when the pulse is on and when the pulse is off. I've already told you that in this scenario, the signal here is high and the signal here is what? Low. So if you complete like this, it means that the cycle is done. And here another cycle is done, here another cycle is done. This is period. Now, when we move to frequency, frequency will be the number of cycles that are able to be completed within a given time. Call it a unit time of maybe 1 second. So assuming this is not actually 1 second being completed here, assume your 1 second is actually here, okay? It means that we are going to count how many cycles are within this 1 second. And I'll count, this is cycle 1, 2, 3. That means that my frequency is going to be 3 over the time. Which time do we have here? It is 1 second, right? It means that my frequency will be 3 hertz, written like this. And sometimes we just write 3 Hz. Sometimes they write it like this. Okay, that is the frequency. So ideally, I would come and now state or define frequency as the number of cycles per second or unit time. But a period is always um, a period is always an inverse proportion to the frequency. That means that if you remove this proportionality symbol, you would have something like a period as equal to 1 over f, assuming your constant is 1. Okay, that means that period t will always be equal to 1 over f. So if I tell you to calculate the period here, you would say t is equal to 1 over 3. And in that case, of course, I don't know. What is 1 over 3? I think, is it 0.33 second? I don't know. What is it? 1 over 3 is what? I think if my math is not wrong, that could be the answer. Is that clear? People on?
Yes, it is correct.
Okay. Yes. Is that clear for each and everyone about the frequency and period? Komhimbo, are you following?
Yes, please, I'm following.
Okay. Now, can you explain to me what period is in your own terms?
Period is the time between one cycle.
Okay. Adrian, what is frequency?
Frequency is the, my God, can you put back there? That's okay. Frequency is basically to have how many cycles in a given time unit.
Okay, that's good. Yes, Emmanuel.
Uh, does it mean a time taken to complete one cycle is
Exactly.
is what is what is the time 1 second that we get to complete the one cycle?
Yes, true
Okay,
that.
thank
Okay. So, okay. Yeah, so that's the whole idea about um, the period and frequency. Now, there is another issue which is called duty cycle. This is mostly a concept that you will find important if you have to program a digital system and then implement um, a motor. You want to increase speed of a motor, you want to increase brightness, things like that. So you handle what is called duty cycle. So what is duty cycle? If I represent my timing diagram like this, and I say that I have maybe different cycles like this, maybe like this, um, and then I say um, this is maybe to complete this cycle was maybe time 1, complete this other cycle was maybe time 2, complete this other one was maybe time 3, this was 0, this was voltage. uh, According to what we can maybe guess here. We could say that in terms of percentage, this could be like, can we give it like 40%? Uh, this time, okay, the percentage of this time to be completed in this, and then this percentage would be like 60. Hmm? So here, when it is 60, the signal is high. When it is 40, the signal is 0. We agree. Here it is 0, here is 1, low, high, okay, like that, like that. And here again, if we try to estimate our percentage here in terms of percentage, this would be like, can we call it 80%? And this could be a 20%. This is maybe, can we give it a 30% when it was off, and when it was on, give it a 70%. So, of course, now it can be clear that I need to do some correction here. Oh, okay. So our 70% is here. Okay. So, um, so what is duty cycle in this scenario? It is the percentage when the signal is high. This percentage here. This is a duty cycle. This is a duty
Yes,
cycle.
hello.
Yes, please.
Yes, uh, the current is at 0, but we are still rating it as it is giving some percentages.
Sorry?
Can you put that diagram back?
It is
I'm
there.
seeing there's where, uh, yes, where there is still 0, but we are giving percentages, 40 percentages, and then the 80 percentages when it is still at 0.
Yes,
I,
that is
I
a
don't
percent.
understand.
That is a percentage of a cycle, of that cycle. The percentage of that cycle to be either off or on.
Okay, yes, okay.
Yes. Can I proceed?
Yes, please.
Yes, and I'm saying that if you have understood that, we are saying that now, when we ask ourselves that now, where does duty cycle come in? Duty cycle is now that percentage when the signal is high. When the signal is high, the percentage itself is now what we call the duty cycle. This is a duty cycle. This is a duty cycle, duty cycle, duty cycle. So in a formula, we shall say that now duty cycle is when the the time is when the time width or the signal is high. So sometimes we can write it like TW, or sometimes we can write as TH to represent that the time percentage when the period is high over the whole time. Because here in this case the whole time here now is this one here. The whole time is this one here, since it is the time that is completed in that one cycle. So you have already understood that T represents period. We agree? We agree or no?
We do agree.
Uh-huh. So this is period, yes, and we're saying that now our duty cycle is going to be this time, this time when the signal is high, time when the signal is high, time when the signal is high, over the whole time, the whole period, times 100%. But it is a percentage, okay? That is why I said that it is a percentage of that cycle time. So if we go back to our slide, I say that it is the duty cycle is the percentage of time the signal is in its high state during one period. A higher duty cycle means that the signal spends more time at one. Mhm. For example, in these signals here, what do we have as a higher duty cycle in these duty cycles? We have A, we have B, we have C. Which duty cycle do we have as the high duty cycle?
Yeah, according to me,
Hmm?
the high duty cycle is at 70%.
It is C. Yeah. So I think you got the concept now. You get the concept? Is there anyone of you who is lost here? Mike, are you with us? Michael, are you with us?
Yes, sir.
You have background noise. Okay, Paul, are we together? Is that clear? Emmanuel, is it clear now? So
Yes, sir.
don't get the formula. Don't forget the formula. The formula is there, like I've been demonstrating. And I've said that you will find this concept very important when you want to program things like microcontrollers, and you're programming this microcontroller in your, of course, circuit, and you want to include a device like a motor or light to increase maybe its speed, brightness, okay, brightness, and that is where now you find um, you find a pin which is supposed to be using pulse width modulation. So why are we now bringing the pulse width modulation? Because per se, pulse width modulation means that you want to adjust the width of the pulse. Modulation means changing or modifying things. The word modulation, like by default, modulation means you want to change, like it means like changing or modifying. Okay, so if we say pulse width modulation, remember in this case of our duty cycle, we are saying that the highest duty cycle here we can see is the one which is having a percentage of 70. It is C, and its width is actually what gives us this knowledge of knowing that this is the highest um, duty cycle. So in programming the motor, you want to maybe say that at this time and this time, I want my signal to be high more than how it is now. So you increase its width, you change the width, and so that when the signal is high, because you want to make it like conduct go fast, so you make it stay in the high state for different situation. So you use this concept of pulse width what modulation. So that is where the whole idea of the duty cycle comes in, and very important. Um, yes, is that fine now? I think there is no question about that now. Martin, are you fine? Are you following? Is Martin with us? Okay, someone look for Martin and ask him whether he's in call or no. Um, then there is another concept which is called transitions. Um, this happens when the signal is halfway between two states. Measurements are taken from 50% of the waveform. For example, the width of high pulse is measured as shown in the um, this figure below. The period it is also measured um, at 50% of these points. Now, in this diagram, you can see that where the T starts from and ends is actually in the in the midway of that. Let me wrap this. So this is what I mean. That you see, this is the midpoint. That of course from here is exactly halfway from here. Okay, this is the same as this. So when you are trying to measure the pulse width, because by default we are seeing the timing diagrams appear like this, right? And we know that this one was our pulse width in that situation. Okay, but if we want to know the transition, how things have transited from one point to another, then we have to take a signal and measure halfway to measure the width. So if we want to this TW means that we are trying to measure the width of this pulse, and we only measure the width of this pulse starting from the midpoints here. You cannot start from here, because in this situation it will mean a different what thing. So this is in the transition is measured in form of SI unit as seconds, because you're measuring the time, how long it takes that pulse to stay on. Okay, so you don't start from here, you start from here. So that is what it means. And also that because you start halfway this side, halfway this signal when it is rising up, when it also goes down like this, you wait until when it is starting to move up again, and now midway is where now you stop to now uh, measure your whole period. So if I want to calculate the whole period, I'll now take my measurement from here, here. Is that fine now? Is it clear? Hello? Someone say something, because I don't want to be adjusting the screens very frequently. Is that point clear?
Yeah, that point is taken.
Okay. So we are not rushing so much because earlier I've realized that people take long to understand this digital electronics. Most of you might have come from backgrounds who are which are not so strong in maybe physics, electricity. Yet this is digital electronics where you are actually supposed to have some basic knowledge about analog electronics. So that's why I'm not so taking so fast. So if we don't finish this slide, yeah, we should be completing it maybe next time. What time is this class supposed to be stopping? Because it's already 12. What time is it stopping? Is it 12 exactly or 12:15?
12:15.
Okay, so we remaining some 12 minutes. Okay.
Actually, by this time, we could be preparing for the next class.
Oh, we should have stopped. What
Yeah.
time is it starting? What time is the next class starting? Is it 12:15 or 12:30? Oh, so I have some 12 minutes. Okay. So, yes, if you have understood the transitions, let's go to the events and ages. So we're saying that an event is considered when the system changes states. So we know a system only has two states, one or zero. So that means that if a transition has happened, for example, from here to here, then an event is considered to also have taken place. Okay, so without a transition, then you cannot have an event. But this event now will take us to an edge. So if you are moving from a low to a high, that means that this is a rising edge. Okay, this is a rising edge. But if I was moving from um, if I was moving again from a high to a low, then that will be a falling edge. So I would say that this one is a rising edge, while this one is a falling what? This is a falling edge. And I'm saying that we call it falling because it is trying to move from a 1 to a 0 or a high to a low. That means that this is what? Falling, yet this is what? Rising. So these are edges, and we have seen that again, we only count that an event has happened if we are able to know that something has transited. So this is a transition that has happened here, then that means that there is an event. Okay, not event, not age, but I mean there is what? There is an event. Okay. Um. Yes. Can we briefly talk about the evolution of digital integrated circuits? So circuits logic means how the circuit actually responds to the input. Um, so in the past technologies, we are using vacuum tubes. Those of you who have read about the history of computers, we know that those earlier computers used actually the vacuum tubes, and later they moved to what we call transistors. Now, transistors what actually inside the digital integrated circuits. So an IC has many transistors inside, but they can be in different families. So later we shall talk about the families of the ICs. We shall talk about the CMOS, the TTLs, okay, many. But this is much about the history. Nobody is going to ask about the history. Yeah, but just for you to understand that that exists. That in the past technologies that were using vacuum tubes, but later as they phased out because of issues like a need of much power, and also that they were becoming hot. You guys can look at those old machines like the Pentium 2s, Pentium 3s, Pentium 4s. Yeah, they used to overheat. That's why they now change to new technologies, which started from the bipolar transistors and now later the TTLs. But also the TTLs are phasing out, and now we are using actually the complementary metal oxide semiconductors. But of course, as technology also relies on the backward compatibility, we still use a lot of the TTLs. Okay, I think this was the table that I earlier talked about. Um, the comparison of the digital and the analog systems. So we have already discussed about this and just now go through. Okay, this is just knowing what are the disadvantages and advantages of both analog and digital. Okay, you will go through. And this diagram was actually explaining to you that the process of converting the signal that you have got as analog to now digital is actually long. It is one of the disadvantages that I was trying to demonstrate in that diagram. Yeah, and I think this brings us to the level at which the physical students are at. Yeah, they stopped at this point of the digital number systems. So I also propose that we should start from here next time. I welcome any questions, clarifications, doubts before we close the class.
Yes.
Okay, yes, Emmanuel.
Hello. When you go back to the first diagram that we have under digital,
Emmanuel,
there's where
I'm
you,
not hearing you.
there's where you indicated false and true.
Sorry?
Under the first table, there's
Mm,
where you indicated false and true.
I remember.
Then yes, somewhere you mentioned this uh, under the last column you indicated bowling. This bowling is it representing only for the true, which is one,
Okay, can
or
I
it
hear
is
your questions your question again? I'm hearing you're talking about the Boolean.
yes, the boolean. Is the boolean
Mm.
for stand for the or it is for the false?
Okay, so Boolean is a way of knowing if that value has to be a zero or a one. So in Boolean, it is just used in manipulation of binary. This is in the base system, the base two system, I mean. Because you see, base two, we only have two values, 0 and 1. You cannot include 2 in base 2. So you either have a 0 or a 1. So if we have a 0, that means the boolean is false. If we have a 1, that means the boolean is true. For example,
Correct.
you,
Correct.
you cannot
I got
say
you.
you cannot say that I went to town, but I'm home. You are either in town or you are home. Okay? So many circuits
Yes,
are
thank you.
going to operate like that. That if you give it, um, if you give it, for example, um, a signal here, an input signal here. Let me take for example, using this. Um, Let me use this gate here. If I give a one here, I expect here, I expect an output here because I have an input. So this output is going to either give only a zero or a one. This zero should be in the boolean a false, and one should be a true. So using this gate here, I'll have my output as a zero because I'm using what is called an inverter. So we shall look at logic circuits, logic gates later, and you have to understand this. This is a NOT gate, or what we call an inverter. Does that help now? Emmanuel, you comfortable now?
Yes, sir. Yes, sir. Thank you.
Okay, welcome. Is there any other doubt? Hello? So everyone is comfortable now, right? Okay. Bernard, you have an issue?
No, no, I
Vivian,
don't, sir. I don't.
Vivian, I've not heard from you. Hafsa, I didn't hear from you. I hope you guys are fine. Okay. Um, as a continuous thing for you to learn, please kindly. Um, Actually, I think I'll have to give you a certain lab and we try it together. But help me to read about the semiconductors and active versus passive components. In this, you will find things like capacitors, diodes, inductors, resistors, and transistors. Of course, before this, you could little bit go through the fundamentals of electronics, and you look at the theory of valence electrons, valence electrons. So just for your personal reading, because you'll later need these concepts to move with you, uh, for you to be able to understand designing digital circuits. I've already told the physical class that digital electronics may not have been specifically for you, but it is just going to be like a support when you find situations where you have to work with maybe digital electronic machines. You want to also program, maybe fetch some data from those machines, because you're learning to be data scientists. But the situations where you need to collect data, and maybe you need to really interface with digital systems. So these concepts might really be important for you. Okay, so if there's no doubt, I wish you a lovely weekend and we meet next time.
Thank you very
Okay,
much.
welcome.